Okay, so last 2 weeks we've been talking about like the K-linear extension and wedge products. So I thought it was natural to start talking about the trace and the determinant and how they like these constructions help us connect them really nicely. So yeah, we're gonna do some review, we're gonna do some proofs, and then like a brief discussion at the end if we can get through everything. Okay, so this is just a brief, like really simple idea of what tensors are, right? You can think of them as collections of expressions of this form where the V's belong to the vector space V and the W's belong to W, that has this multilinearity property. So like if I have lambda 1 V1 plus V2, I can split this along the tensor product. And if I had this going on in every single like coordinate, I would do that for everything. So it's multilinear. Hopefully we're comfortable with this by now. Also, if you have questions, please interrupt at any point. Um, I thought it was nice to kind of like maybe think of tensors and like the larger scheme of where tensors fall in the kind of compositions that we've been creating. So like I guess the first composition of things you to think about is like a Cartesian product, which is just like you're considering tuples of the underlying set without any algebraic structure. And then you maybe look at the direct product between vector spaces where suddenly like the tuples now work as vector spaces and you're doing things coordinate wise. And then, this is something that confused me in the earlier presentations, but direct product and direct sum are basically they are the same thing for finite like compositions. It's only when it becomes infinite that the difference arises. And the difference is that direct sum only contains tuples with finitely many non-zero components. That's not super important for this, but I think it's just good to see it. And then tensor products are tuples with that multilinearity property. And because of having multilinearity, it actually makes it like a higher dimensional space. Like so the constraint that kind of arises there. Oh, thanks, Aiden. Yes. Um, yeah, it makes it so that like the dimension of the V tensor W is dimension of V times dimension of W. And then you have the wedge product, which actually, it's good to realize, I mean, that's going to be important for our discussion here. That can only be done with a vector space in itself. So you can't vector V and W, or you can't wedge V and W together, because then the idea of anti-symmetry wouldn't hold. So you have tuples with multilinearity and anti-symmetry. So in putting these constraints on it, it kind of makes it a more constrained operation. So, okay, now let's think about like the exterior power. So maybe you don't just want to wedge V with itself once, but multiple times. Then the exterior power consists of like collections that look like this, and they obey multilinearity and anti-symmetry. So same multilinearity property, but then if I apply a transposition to any of the two elements in this kind of ordered exterior product, then it negates it, right? So then we could use the idea of like any permutation can be split into its transpositions, and then I can get like a sign very easily from any permutation of the wedge product. So the important properties that come out of this is one, like it has to vanish if you have like V wedge V. So any repeat in the wedge product will create zero because it has to be the negative of itself. And you also have associativity pretty easily. Something else to keep in mind is just that like not every element in this wedge product is reducible to a single like wedge product. So in general, you'll have like sums of wedges. Yeah. Okay. Now this is a really important construction that Aman showed last week. Let's review. So if you have an endomorphism, so it's a homomorphism from V to itself, let's call it A, then you can kind of think about applying the wedge product to a linear map and not just like to the space itself. So this is like the wedge product of V, but then this is the K-linear extension of A, which is a endomorphism of V, right? And so it's parameterized by this K here and this N. So this is just like telling us where the space is. So we're going from lambda NV to lambda NV. And this is telling us how many times we apply A on the different sections of the wedge product. So that's where you have this like lambda M AK of some wedge is going to be, I mean, this is kind of, I guess, hard to parse if this is the first time you've seen it, but this is like the nice kind of way of writing it. So you're choosing where to apply the A, right? Because if it's A to the 0, then you're not applying it. If it's A to the 1, you're just applying A. And you're applying it to J different entries of the wedge. So this creates certain like dimensionality restrictions. So like, or just like the number of things that you're adding up will be bigger as you're like in the middle, like because it really is like N choose K is like the number of things in this sum ultimately. A nice illustration of this is like wedge 3a1 will be I'm applying a to each of the coordinates in v1, v2, v3. Yeah, who is iPad? Anyways. Yeah, and if v is n-dimensional, the dimension is n choose k. And you can consider, applying a to maybe if you do 2, then it would be 3 choose 2, which is 3 again. And then, you apply the a's like this. Now, this is where things get like tricky, and this is where like a deep understanding of the k-linear extension is really necessary. So you can define the determinant and the trace really easily from them, but it takes a little work to realize how this happens. So the determinant of an endomorphism, just think of it like a square matrix, is the number by which any non-zero tensor omega in wedge n, this should be wedge nv, by the way, that's a typo, is multiplied when you apply the lambda n an, like the n linear extension, or the n linear extension. I'm not sure what to call it. So this pops out of the omega. So it's kind of remarkable. I mean, it's not even trivial, like, to begin with, that like, it's just a scalar multiplication. I mean, the reason that is because this is a one-dimensional space, and so all linear transformations of a one-dimensional space are are just a scalar multiplication. And I'm going to show you how the determinant pops out. I'm also going to show you how the trace pops out. So the only difference between this definition of the trace and this definition of the determinant is that we're doing wedge n a1. So we're applying a to only one coordinate at a time, and we're summing up all of the different ways I can put a on each of the coordinates. And the trace pops out. So let's see, like, this is probably the nicest way of writing out how this happens, because there's a lot of things that happen. So wedge n an of omega is, so omega is just some wedge of v1 through vn. So then I apply a to each of the parts of this, each vector, and then I write each of these products as sums. So the matrix product of a v1 becomes this and this, and then I pull out the sums due to multilinearity, and I'm also able to pull out all of the a's as well. And then what happens is that now we have this like indexing of j1 through jn, which is inside this sum. And we know that this is only going to be 0. So this is only going to be non-zero if there's no repeats. So these have to make up all of the different permutations of v1 through vn. So that's how we come to sum over like all the permutations. We have to consider the sign of the permutation because of the anti-symmetry property. So this is how we're keeping track of that. And then the product of all of the a's with so aj sigma j is coming from this. So really we can think of these j1s as like we're picking out all of the maps j1 that become permutations. And then this is just the classic. So we then we get the v1 through vn back here. And then this is just the classic, I forget who this is due to, Cauchy, or no, someone's famous basic determinant identity that you learn in linear algebra. The trace is a very similar way of getting about it. So you apply a to each entry in the wedge product. So you have this sum, and then you express this as a sum, and you apply multilinearity. And then you notice that this thing, again, you apply that idea of the vanishing property. So this is only non-zero if vji is equal to vi. This should not just be I. So this eliminates the second summation altogether, and then you just get this like trace being the sum of the diagonal entries of the matrix, right? So the trace and the determinant pop out really nicely from the wedge product, and that's part of the reason why we like the wedge product. A nice thing before we get into some of the other theorems that relate to trace and determinant is that, like, maybe something I should have made a slide about, is that like this opens up a whole like discussion about what happens in between like wedge n a1 and wedge n an. And so these turn out to be like this whole family of different polynomials in terms of in terms of the coefficients of the characteristic polynomial. So you might be familiar with the idea that like, and this is all like Vietta's formula really, because the determinant is the product of the eigenvalues, right? The eigenvalues are the roots of the characteristic polynomial. So it's the last term in the characteristic polynomial. The trace is the sum of the eigenvalues. So then it's like the linear term in the polynomial. But then you can consider more and more, or is it the linear term? Yeah, I think so. And then you can keep on going higher and higher, and then you get these kind of symmetric polynomials in terms of the eigenvalues, which turn out to it's a whole unnamed family, or maybe people apply names, but they're not that well known. So yeah, this really opens up the imagination. Okay, now these are two really famous identities about the relationship between trace and determinant. So the first one I'm going to show you is called Liouville's formula, or Louisville's. I've just called it Louisville's in my head. So if you take an endomorphism of V, then you have that the determinant of the matrix exponential of A, so it would, we could write it out like this. So importantly, if I express A as a matrix, it is not me taking E to every single component of the matrix. It is me applying the Taylor series to the matrix itself. So the determinant of the exponential of A is equal to the exponential of the trace of A. So this is actually like a numerical exponential, whereas this is a matrix exponential. But this is, of course, like this is an awesome formula. You can derive this really easily for like a diagonal matrix, but the general proof will require a bit of work. And also, like, the more general statement of this is that we can add some like formal variable t inside of this. So the determinant of the exponential of TA, so then this would just change accordingly, would be the exponential of t times trace of A, where t is a formal variable. So we have this formula, and then we have Jacobi's formula, which is a little more complicated. And it says for A so a function of t, an operator valued formal power series such that A inverse exists. So maybe this was poor notation because A of t is actually quite a bit different from A here. But I'm going to explain like what an operator valued formal power series is later. Maybe I should have explained it in this slide. But anyway, you have this relationship that is effectively the derivative of the determinant is something in terms of the trace of the differential with some extra terms floating around. Yeah, so we're going to prove Liouville's formula, and Jacobi's formula will be an important lemma on the step on the way to that. Which is interesting because you might have expected the opposite, like, oh, this looks way more complicated. Maybe we would use this to prove this. But no. Any questions so far?
I guess this like A inverse, is it like an A inverse of t, or is it like A inverse of 0, or
It's A inverse of the formal power series. So
okay.
we're going to show something to this effect. This is also wrong. What I mean to say here is that like 1 plus x times 1 minus x squared. You know what formula I'm talking about? Like an infinite product times 1 plus x will just become 1. Oh wow, I should have finished this slide. Yeah, but that's what I mean. Like I'm saying if there's another formal power series such that if I multiply by it, it'll be 1.
Oh, okay.
Wow,
Yeah, that makes
okay. Okay. Okay, so the game plan is we're actually going to use like differential equations here, which you might not have expected. So we're going to express both determinant of exponential of A and exponential of trace of A as formal power series in T satisfying some differential equation. So first we're going to establish some lemmas about how to solve differential equations for formal power series. And then we're going to guess a suitable, well, I mean, guess not in quotes, like I guess we are, a suitable differential equation that will enable us to prove the identity. Okay, so I guess the first thing we need to know is maybe like, okay, if I have f of t is equal to exp of t a, so this is an operator valued formal power series. So what I mean by operator valued, by the way, is that the coefficients of the power series are themselves linear operators. And t is the variable this is the formal variable that like creates the series. So yeah, this is the unique solution to the following differential equation. So this should kind of look familiar, right? If I'm taking the differential of f with respect to t, or this is just the derivative, then it's f of t times a. So an a pops out of it. So it should be kind of natural that this is like exponential, right? Because it has that kind of, it's basically just the derivative of itself, and then this factor is popping out. And then you have an initial condition that f of 0 is just equal to the identity morphism. Identity, oh my God, what's the word I've been using? Endomorphism. Okay, so the way you prove this is not too hard. So you have f of 0 is equal to 1. Therefore, you know that f of t is going to be 1 plus a bunch of other things that are function that have t attached to them. Makes sense because if I evaluate it at 0, all the t things are going to die. So if I differentiate this with respect to, if I just differentiate it once and then evaluate it at 0, I get a because of this. So f prime of 0 is f of 0 times a, which is f1 times a. Sorry, that should be f1 times. I mean, okay. The idea here is if I differentiate this with respect to t, so this term goes away, this just becomes f1 and everything else is in t. So then if I evaluate it at t, it just becomes f1. So I think, this should be gone. This is just f1 is equal to a. I should typo these more. I should not typo these more. I should not put as many typos. God. If I differentiate with if I take the second derivative, then a squared pops out because, and then this is equal to 2 f of 2 because of the 2 that comes out here, right? And then similar things happen. So I have a cubed, so the a's just keep stacking on each other as I take derivatives and evaluate at 0. And then that's due to this formula. And then the 3 factorial, the 4 factorial, etc., that's going to pop out from the differentiation of, a polynomial, really. So matching coefficients, so what is f2? F2 is a squared over 2. What is f3? F3 is a cubed over 6, and so on. So you can solve by matching coefficients, and then you get exactly the exponential of t times a. So we've shown that given this, you can extract that f of t is equal to x ta, and the other way around is like trivial. So therefore, we've shown that it's the unique solution to this differential equation. But that's the first thing. The second thing is a little kind of boring and technical. It just says that if you have, again, 2 power series in T with coefficients from these wedge products, so it's an operator valued formal power series in T, then the Leibniz rule holds. So basically, like, the derivative acts like it should. The derivative of the wedge product is equal to the wedge product of the derivative applied at each element. And this happens, well, you can argue this easily just by using the fact that the derivative is linear and the power series can be differentiated term by term. So I only really need to look at, like, terms of this form. I don't have to look at, like, linear combinations. I don't have to look at the whole series. I just can look at, like, singular terms. And oh my God, another typo. This should be a. T to the a omega 1, t to the b omega 2. So then if you just do it out, really, you get this clearly, just like this is popping out. And then if I evaluate the other side of this, I get this, and then these are the same. This is by multilinearity again, because I can put this TB here and I can put this TA here, and then I split the A plus B and I get the 2 terms that I want, right? So you should believe me. This is nothing crazy. This is nice. Okay, the second thing is that, the third lemma is that the inverse of a formal power series exists if and only if phi of 0 is not equal to 0. And for this, you have to invoke the identity that I just completely botched over here. Let's actually write it out. So you have 1 plus x times, like, 1 minus x squared. Right? The reason this is going to just cancel everything except the 1 is that, like, I'm recreating this and then I'm adding up. Well, actually, maybe this should be an alternating series. No, I'm forgetting. I think it should be. It should be this, minus x cubed, ... Right? So these are like inverses in power series land. So the whole point of this is that if phi of 0 is not equal to 0, so if you have, like, some non-zero first term, then you can kind of invoke this relationship, this property, because then, so phi of t can be expressed as this. So it has this this constant term, and it has something in terms of t. So, and psi is just another power series. So then we can construct the inverse explicitly by saying, okay, 1 over 5t is equal to some constant, and then 1 over basically 1 plus x. And then we could just take this x and then bring it over here and then do what we want, and then express it. And then this is the inverse. So we've just explicitly constructed the inverse for the formal power series. Right. Again, this is kind of surprisingly boring. But you kind of need it. Any questions so far? Okay. Cool. So now we're gonna do something interesting, and prove the Jacobi's formula using what we've done so far. So okay, an operator valued formal power series, as I said before, is just a function f of t equals 1 plus f1t plus f2t squared plus dot dot dot, where the coefficients are linear operators. So then Jacobi's formula tells you that if A is an invertible operator valued formal power series, then we have this relationship. I really should put T's here because we're talking about not a matrix, but again, an invertible operator valued formal power series. If you go to Wikipedia and look up Jacobi's formula, you're going to see like 5 different ways of writing it. Like sometimes I think the way Wikipedia shows is using the adjugate, which is the transpose of the cofactor matrix. I think that's kind of an ugly way of writing it. I mean, I think the complexity loss here, or the complexity trade-off we have here, is that we're talking about formal power series. So I think like that's kind of hiding things under the rug. Because I mean, I guess like the clickbait way of talking about Jacobi's formula is like, oh, the determinant of the derivative of the determinant is the trace. So if someone says that, you should be like, no, you're clickbaiting me. It's a little more complicated than that. Yeah. Okay. So how do you prove it? It's all definitions, my friend. So start with this del t determinant of a of t. So that's being applied to some omega. We want to show that this does the same thing to omega as this. So then you have this property, which is that the derivative of the operator is equal to the derivative of the operator as an operator acting on omega is equal to the derivative of the operator itself acting on omega, which is a non-trivial thing, I guess, but we're kind of going to gloss over it. And sorry, this should be like a of t and omega, but we're going to drop the t for now. So now that we have this, we can actually, be more honest. Like, what is the determinant of a omega? Well, it's this, right? So if omega is v1, v2, v1, v2, dot dot dot. So then then it's like the wedge n. So it's equal to just doing wedge n an v1 dot v1 wedge vn, or just omega. So that's where we're just applying the definition of the determinant from this step to this step. And then we're applying the Leibniz rule from this step to this step. So that's where the summation comes into play. Right? So we're applying, so it's product rule, really, is what we're doing. So yeah. So the nice thing is, like, if you're kind of familiar with the notation that we've been keeping up, like this almost looks like what we want, which is a trace, right? We want a trace on this side, right? But the annoying thing is that there are these A's here, right? And we really want these all to be clean V1 through VKs, so that like there's just an omega, because ultimately at the end we're going to want to pull out an omega and see what the factor is in front, or whatever the operator is in front. That's going to be this. So the way you do that is you invoke this thing, which I guess we haven't covered yet. So I might recommend it for the next presenter to talk about, which is called the algebraic complement of A. I don't want to get too much into the theory of it, partly because I don't know anything about it, but I do know that the algebraic complement of A for an invertible matrix is the determinant of A times A inverse. This might actually be, no, wait, not for a matrix. What I mean is a formal power series, operator valued formal power series. And there's a more general formula that we won't think too much about. But I really just want to think about it like we're invoking like the matrix adjoint, kind of. So you may remember from uh like linear algebra this idea of like the adjoint. So like if I have let's like AV, so I guess it was something you learned with respect to like inner products. So it's like inner product of AV comma W is equal to like V comma like A. Does anyone remember the symbol for an adjoint? I guess transpose, something like this.
Is it like the dagger or something? I don't know.
Oh yeah, maybe it's like the dagger. Yeah. So yeah, that's close. Okay, so this is basically this idea that like if you have some inner product, or in this case, I guess a wedge product, which is quite different, but let's pretend they're similar or the same. Then you can kind of do this thing where like you're swapping out where this matrix is being applied. So in this case, we're actually like just we're able to move all these A's out and then put them into this. So there's this magical thing called the algebraic complement, which allows us to do this. And I kind of hate that I have to hand wave that, but it was something I figured out kind of late in my construction of this presentation that we haven't covered this. But I leave it to you. And maybe it adds a sense of mystery to this proof. It's like now I want to learn more. So that's what I hope the effect is. So yeah, so now we've expressed it as a trace type thing, which is great, right? Because now we're just summing over the application of this operator on each of the V's. So then that's kind of exactly what we want if you look at things carefully, because then you get it's basically so this operator is equal to the trace of this, and then you apply this, and then you get this. This is not an effective way of teaching. So then you have the trace of the determinant A inverse delta A, delta TA, and then you can just take out the determinant because the trace is, the determinant is just a constant here, and that factors out of the determinant. And then you have exactly what you wanted. So that concludes the proof, or like the hand wavy proof of Jacobi's formula, right? The derivative of the determinant of this operator valued formal power series is the determinant of it, uh, and then the trace of A inverse delta T A. It's a mouthful. But now that we have this, I think maybe the nicest thing is we've established all the work. Liouville's formula actually passes in this really nice way. It's one of those proofs where like you don't feel like you're using that much, but you're kind of slipping. Like you have one way of doing things and it kind of slips into a new way of doing things and you barely even realize something happened. So it's like kind of like a sleight of hand. So let's read it really carefully. No, I shouldn't do that. Okay. F of t. Let big F of t be the exponential of t times a. F of 0 is 1, clearly. So it's invertible by lemma 3. So then we could apply Jacobi's formula, because Jacobi's formula only applies to operator value to what's the word? Invertible operator powered formal power series. Operator valued formal power series. So if you apply Jacobi's formula to this big F of t, you get this. And now what we're going to do is, so we had some differential equation characterization of this, as we mentioned before. So which said that the derivative of f is equal to f times a. So that's all I'm writing here. The reason I'm looking at f inverse times this is just because that's here, right? So we want to rewrite this in a nicer form. So we apply f inverse delta t f. That becomes f inverse fa, which can be associative, whatever, becomes this, and then just becomes a. So this is actually just a because of the way we defined f. So think about it. We started with Jacobi's formula, but we chose something to input into Jacobi's formula such that we could apply its differential equation and get a different way of writing it. So that is what happens here. So now we have trace of a instead of trace of this somewhat nasty thing. Okay. And then we're basically done, actually, if you just choose your perspective carefully. So little f of t, let's call little f of t whatever det of big F of t is. So now we're just talking about like a number, just a number. So then if we just put little f of t into this formula, we get this, right? I'm literally just replacing variables. And if you look at this is kind of, well, it's exactly the characterization of the exponential, but for like a normal, like just a, the normal exponential we know and love. I mean, it's the same formula we talked about, but it's just the derivative of f of t is just f of t times some constant, and the constant here is trace of a. So then if you apply that, then you know that little f of t is equal to actually the exponential of t times the trace of a, and therefore, and then little f of t was equal to this, but this was equal to this. So then you have that the determinant of the exponential of t times a is equal to the exponential of t times the trace of a. So that's our proof. So yeah, it was really about a clever application of the exponential and then being really careful about some of your rules of formal power series. Any questions? This took me a while to wrap my head around. But okay. Here are some related things to think about. So in the book, it's presented such that this is like an exercise afterwards. So kind of think about like the anxiety you would have if I gave this to you as a homework problem for a class and you're like, oh, I have to do this for homework. So for p less than or equal to n, where n is the dimension of v, and a being an endomorphism in v. Oh, I shouldn't write that. It's not an endomorphism of v. My bad. It's an operator valued formal power series with entries in endomorphism of v, or with coefficients in endomorphism of v. Then Liouville's is the special case of this formula. So if think about it, so we have this formula in general, which might be like hard to parse. Think about it, if p equals n, what happens? Well, wedge n, whatever n, is determinant of that. So determinant of exponential of ta is equal to exponential of t. What is this? Wedge n a1. That's trace of a. So, checks out. So this is the more general view of what's happening. I think the proof should be the same stuff going on. So if you really want to do it as an exercise, like follow this kind of approach. Actually, not just this approach. I'm pretty sure what's happening with this adjoint is really important. That's because that's kind of how we're translating between like one thing into a trace. But whatever. And then there's also Sylvester's theorem, which I actually don't know how to prove from this directly, but like I have heard of it, and I think it's kind of an interesting identity. It tells you that the determinant of I plus BA is equal to determinant of I plus AB. And I guess if you really think about this hard enough, like the reason why this is weird is because these are happening in different spaces. So we're taking the determinant in different spaces and we have this nice correspondence. So that's quite nice. Something to look into. Another thing, so kind of what inspired me to do this presentation was something that Aman mentioned last week. I think Aman and Zach were talking about this. There was like this nice little exercise, or I guess it's like a little, I called it a vignette in the differential equations textbook that kind of shows an intuitive feel for what Jacobi's formula is about. And this is kind of where the clickbait comes in. So let epsilon be some like little error that we're applying. So if we have like the determinant of I plus the error times some matrix, so a really small taste of some other matrix, then you get this. So it's one. So one is the normal thing. And then the noise, the way that noise is playing out in like the first order epsilon term is the trace of A. And then everything else is epsilon squared. So it's, it's meaningless. We don't care about it. So we can view this identity, or we can prove it just using the eigenvalues like pretty easily, right? Because the determinant of I plus epsilon A is equal to the product of these are the eigenvalues of this matrix. So 1 plus epsilon lambda I. And then you note that, well, the first term, or the zeroth order term, is just 1. So if I apply 1 on each product. And the second term is the sum of all the eigenvalues, which is the trace, and then times epsilon. So that's where this linear term in the trace is coming in. And then everything else is epsilon squared. So it's smaller. So how does this relate to Jacobi's formula that we saw? Let's maybe go back. So it's saying that so maybe let's gloss over the idea of the formal power series again. So the derivative of the determinant, I guess the determinant of this matrix, which is just a sum of a bunch of other matrices, which are functions of t. So the thing is, you're taking the differential with respect to this t, right? Then what comes out is the determinant of A times the trace of A inverse delta TA. I think what's important, yeah, what's important is really like the trace of whatever's happening here. Um, to be honest, I don't have a great way of explaining this outside of just the derivative of the determinant being related to the trace. Um, maybe I think playing around with the numbers and actually like maybe looking at what happens when you differentiate like this can maybe show you something. Um, yeah, yeah. Uh, anyways, so yeah, that's just a kind of an easy way of thinking about it. Um, and yeah, I mean, I just want to finish off by saying that like there's a lot of other nice identities out there. There's like just fields of them. But you can look at the duality of determinant and trace in two ways, right? Because like there's many ways to develop a theory of linear algebra, as Winitzki shows us. He's doing a kind of a fresh way through exterior products. So you construct linear algebra, and then your constructions have these like immediate like sometimes you make your constructions out like based on these observations. Like for example, like I think part of the reason the wedge product was kind of created the way it was to like make it really easy to state things like that relationship between the trace and the determinant. But then, wherever you're starting with your analysis, like or starting with your constructions, they're always going to be a little farther from maybe what you're trying to prove. So you can start in a bunch of different places and then you kind of go outwards and then make the theorems. And the nice thing about this duality is that it really holds. Like the more distance you get from like your construction, like it's still coming about. So that's cool. And yeah, I just think carefully understanding all of these constructions was key. And I think I'm kind of hypocritical to say that because we don't really know what the algebraic complement is. But other things, I think like the wedge product, I think it's great that we've been reading about it and because it's powerful as we've seen. Um, so yeah, I'm gonna end it there. Yeah, thanks for listening.